Welcome to today's video where I'm going to go through how to simplify radical expressions. A lot of this will draw upon some prior knowledge from your introduction to radicals in Nerf 10. So I'll just start with some of the terminology that goes along with radicals. So here's an example of a radical. I'm just going to make this a bit bigger so we can see it. Okay, so this radical has what's called a coefficient, a radicand, and an index. The number under the radical sign, that's referred to as the radicand. The little number up above here is called the index. And the number out in front here is called the coefficient. Alright, so when I refer to any of those, hope you know what I'm talking about. If you just have square root, let's say, of 25, this is what they mean by a radical. When there's no index here, you don't have to put it in. It's understood you mean 2. Right? That's understood to be 2. Basically, the index tells you how many times you'd have to multiply the number by itself to get that value. So if I see the square root, I'm trying to figure out a number that I multiply by itself twice to get 25. So the answer would be 5. Versus the cube root of, let's say, 8. So now I'm trying to find a number that I multiply by itself 3 times to give me 8. The answer in this case would be 2. Alright, so that's just some of the vocabulary. Something that you probably have not heard tell of is what they call a restriction on a radical expression. And the reason there are restrictions on radicals comes down to the notion that you cannot take the square root, let's say, for example, of negative 25. When we were doing our unit on quadratics, you would have found if we were doing the quadratic formula, let's say, and we got a negative underneath here in our discriminant, we would say, well, that's not possible. There's no solutions. So this is impossible, which generates the need for us to identify what are called restrictions. So restrictions is simply our way of saying we want to make sure that we don't get negatives underneath square root signs. Now, I got to go back and clarify that. What if I had the cube root of negative 8? And I said to you, could you do the cube root of negative 8? You can actually do the cube root of negative 8 because it would be negative 2, which would be negative 2 multiplied by itself 3 times. Negative 2 times negative 2 times negative 2 is negative 8. So let's backtrack on what we said here a moment ago. When we're doing radicals, if the index is even, that means you're going to multiply the number by itself an even number of times. It would be impossible to get a negative. If the index is odd, we would have no issue with the radicand being negative, so there would be no need for any restrictions, versus an even index where there is going to be a need for restrictions to make sure that we don't get a negative underneath a radical. Alright, so if I look at the 6 that I've got, or sorry, not the 6, I got 3 or 4 here. The square root of x. Well, the square root of x underneath the radical, the radicand, x, in this case has to be bigger than or equal to 0. You say, well, why is that? Because you're not allowed to have a negative, because the index, you say, well, there is no index. Sometimes students mistakenly say, oh, the index is 1. When there's no index on a radical, it's assumed it's a 2. Therefore, that's an even index. You can't have a negative value here. Index is 2, which is even. The radicand, so the radicand has to be, that means whatever's underneath there must be bigger than or equal to 0. Well, now you just solve this and say, well, that would happen if x was bigger than or equal to negative 7. This one is an odd index, cube root. I would have no issue with x being any type of a number in that one because the index is odd. Here's another even index. So an even index, I have to make sure that underneath here is, let's just write it out here, 6th root of 5x to the 8th. This is a bit of a trick one. This is not allowed to be negative, but it wouldn't make any difference what I put in here for x, because whatever I put in for x, I'm going to raise it to the 8th power, which is an even exponent, which is going to guarantee that's positive anyway. So this one, even though it's an even index, I could still say x could be any number just because of the fact that whatever I put in there for x is going to get raised to the 8th power. Now, to do these restrictions, it's dependent upon you remembering how to solve a linear inequation. Well, linear inequations are solved the same way. Let's say this had been 4x plus 5. Instead of an inequation, it's an equal sign here. Well, you would solve this by getting the x's on one side. So it would be 4x subtract 9x, be 10 subtract 5. So negative 5x would equal 5. Divide by negative 5. X would be negative 1. That would be an equation. This is an inequation because of the inequality symbol. It's done the exact same way. You collect the x's on one side, 4x, take away 9x, put your symbol, minus 10. Oh, did I screw that up over here? No, I just wrote it down wrong. Okay, so minus 10. Bring your 5 over, it'll be minus 5. A negative 5x is greater than a negative 15. Got my x. Now, there's one little catch. You must reverse your inequality under two scenarios. If you multiply or divide by a negative number, you have to reverse the inequality. So for me, in this question, to finish it, I have to divide by a negative. Divide by a negative. X, you reverse your symbol to point the other way. So that would be the solution to that linear inequation. Now the ones we're going to solve are going to be not even going to be as difficult as that. Not that that's very difficult. Let's revisit restrictions. So if I look at each of these four radicals that I have, this first one, the square root of 3x plus 5, that's an even indexed radical. So as soon as it has an even index, there are restrictions. You say, well, what are the restrictions? Underneath the square root sign, which we refer to as the radicand, write out the radicand, must be bigger than or equal to 0. It's not allowed to be negative. And now you solve this to see what x values will make that happen. So 3x would have to be greater than or equal to negative 5. Divide by 3, divide by 3. X would have to be bigger than or equal to negative 5/3, or else you would get a negative number underneath there. So that would be what they call the restriction on x in this question. Odd index, no restrictions. We could care less. X could be any number I want it to be. Even index. So with an even index, the radicand must be bigger than or equal to 0. Bring your 5 to the other side. To get x isolated, I need to divide by a negative 3, which means I must reverse my inequality to face the other direction. So it goes from greater than or equal to the less than or equal to. Even index, but this is the same as the one we already had earlier. It doesn't matter what I put in there for x, I'm going to raise it to the 8th power anyway. So even if I did put a negative number in there or a positive number, it would guaranteed turn out to be positive anyway. All right, so that's how so I can grab any radical. We should be able to very quickly say, okay, here is the 6th root of 3x plus 4. And I could say to you, state any restrictions. That means what is x, what kind of numbers can I accept for x? Well, because it's an even index, the radicand must be positive, which is what greater than or equal to 0 means. Solve this. Divide by 3. Divide by 3. Now notice I didn't reverse the inequality because I was dividing by 3. Students sometimes mix up and say, yeah, you're dividing into. I didn't say dividing into when you divide by a negative, so that would stay the way it is. Now compare that with me changing one little thing, the index, to 7th root. Well, now it's odd. You can have negative radicands with an odd index. So in this case, there's no restrictions. X could be any number I want it to be. That's all I want you to get out of this first discussion on restrictions of variables. Okay, continuing on to our introduction, I need you to recall some things from grade 10. if I have the square root of x, first thing you should know how to do is how to switch that to an exponent. What exponent means square root? Well, you should know that square root is the exponent 1 over 2. Cube root of x, that is the exponent x to the 1/3. Fourth root of x, x to the 1/4. You get the idea. Again, this is not new. I'm requiring you to demonstrate your prior knowledge. What if I had the fourth root of x to the 7th power? How do I write that as a radical? Well, or sorry, as an exponent. It would be x to the 7 over 4. Now you should be able to go in the other direction. If I said, what's 8 to the 2/3? What does that mean? That means, so the bottom number is always the index on your radical. That means take the cube root of 8, and then you can either have the exponent under here, this would have also been true, the fourth root of x, get your answer, and then raise it to the 7th power. So notice these three are all the exact same thing. So this could be written as the cube root of 8. After you get your answer, square it, which could also be written as the cube root of 8 squared. They all give you the same thing. This one's just a lot easier to do because you can do the cube root of 8, which is 2, square your answer, which is 4. This one you have to do the cube root of 64, so the number's a bit bigger, which is still 4. Okay, so fraction exponents are radicals in disguise. Now, the next thing we want to look at is switching between mixed and entire radicals. Again, we're going to concentrate in the beginning here mostly on square roots. So to do that, you need to be very familiar with what are called the perfect squares. And the perfect squares are, well, 1, because it's 1 times 1. I'm not going to count that one. 2 squared, which is 4. 3 squared, which is 9. 4 squared is 16. 25. 36. 49. 64. 81. 100. That's 10 squared. 121. It's 11. 144 is 12. 13 is 169. It's usually going to be one of these numbers. If you have one of these numbers, the reason these are significant numbers is because, for example, 49, if I pick that, the square root of 49 is equal to 7. It's a perfect square. You get an integer number here, a nice whole number. So what we try to do with these is we try and find, so if I see 50, I'm going to rewrite 50 as 2 numbers multiplied together that give 50, but one of them needs to be a perfect square. So I look over my list, and sometimes based on the numbers, like you can kind of pick and choose. So there's 50 is only, well, 36 isn't going to win it, but like it's only these ones you're going to have to pick from to see which ones go into it. 50 can be written as 25 multiplied by 2. Now again, I'm showing every single little step here in the first one. Well, you can, anytime you have 2 radicals or 2 numbers multiplied under a single radical, you're able to write it as the product of 2 separate radicals. And this is why we picked 25. So someone said, well, why don't I use 10 and 5? Because neither 10 nor 5, I'm going to be able to do this and then get here, what's the square root of 25? Well, it's 5. And then you have your radical 2. 9 times 5, 45. Radical 2. Let's do a couple more before we get to this one. Let's do the square root of 20. So I want to simplify that. All right, try and find the biggest possible perfect square that will go into 20. It's only 4, so it's 4 times 5. The square root of 4 is 2, so it comes outside. The 5 is not a perfect square, it stays underneath. In an ideal situation, as you get more and more comfortable with these, this line should start to disappear. you should look at radical 20 and write it down as radical 5, or 2 radical 5. I think on our test, one of the radicals, the last one on quadratics, come down to be radical 40. So I wasn't holding you responsible to simplify radicals yet because we hadn't covered it. But I would expect now students could look at this and say, okay, 40, I'm going to use 4 times 10. Square root 4 times the square root of 10. The reason I picked the 4 is because the square root of 4 is 2, and then the 10 comes second. Now my personal preference is I always put the perfect square first and then the other number second, just so that as I work down the page, they all kind of line up and you say, oh, I see why 4 became 2 because I took the square root of 4. I see why 5 stayed under the radical because it wasn't a perfect square. So I always put the perfect square first so that it lines up as I go down the page. Okay, let's go over to 72. Now 72, the biggest possible perfect square that goes into 72 is 36. And then the square root of 36 is 6, and then the 2 would stay below that. Now what often happens with this one, if we were in class, somebody'd say, I use 9 and 8, is that okay? And I would say, it is okay because 9's a perfect square. So student B says 9 times 8. The square root of 9 is 3, radical 8. This is equivalent of what you would have done. Let's imagine that I had the fraction 12 over 24. And one student said, I reduced the fraction for you. I did this. I reduced it to 2 over 4. I would say, yes, you did. You did a good job of reducing the fraction. Unfortunately, you haven't reduced it all the way. 2 over 4 still reduces. That's the equivalent of this in radicals. This does work. 9 times 8 does give me 72, but you didn't pick the biggest perfect square. So then when you get to here, you'd have to say, oh, wait a second. This still has a perfect square that divides into it. So I'd have to keep going. So I would just go, okay, well, get rid of this out of the way here for a second. So 8 is now 4 times 2. The square root of 4 is 2. And you'd still have your 2 underneath. 3 times 2 would be 6, radical 2. Now let's just jump to a blank page here and do a few. So here would be a few radicals simplified. So I'll just write out 5 or 6 of them. So you might want to pause the video and try them yourselves. So let's go square root 27, 3, square root 300, negative 2, square root 50, square root of 48, square root of 98 maybe, and then 5, radical. Let's put 24 here. Okay, so here's 6 radicals. So if you want to pause the video and try these on your own, it'd be a good idea. I'm going to now go through the solutions. Okay, 27. 9 times 3. The square root of 9 is 3. Leave your perfect square, the non-perfect square underneath. Now this one has a coefficient in front, so leave it. 300. That would be 100 times 3. The square root of 100 is 10. And then you multiply these two together, 30, radical 3. 50, 25 times 2. The square root of 25 is 5. 2 stays underneath the radical. Multiply these together, negative 10, radical 2. 48, 16 times 3. Someone may say I use 4 and 12. You can, but it won't be reduced as far as possible. You'd have to then reduce radical 12. So the best option is go 16 and 3. The square root of 16 is 4. 3 is not a perfect square. It stays underneath. 98, 49 times 2. The square root of 49 is 7. 2 stays underneath your radical. 24 would be 4 times 6. Square root of 4 is 2 times your 5, 10, radical 6. Now, if I just back up to my slide, so those are square roots. Well, the index can change. So I've got a cube root, and here I've got a fifth root. So the cube root of 48. The difference is, now instead of trying to find a perfect square that divides into 40, now I'd have to look for a perfect cube. So the nice thing is, once you get to these higher indexes, they're usually fairly easy to find. It's usually either 2 cubed or 3 cubed or 4 cubed or something like that. So this one, a perfect cube, so the first perfect cubed is 2 times 2 times 2 is 8. The next perfect cube is 3 times 3 times 3, that's 27. 4 times 4 times 4, that's 64. 5 times 5 times 5, 125. It's usually one of those. When I get to a fifth root, you may say, well, I don't know any perfect fifth roots. And you don't have to know any, but you need to know how to make them. Say, well, what would 2 to the fifth power be? It would be 32. What would 3 to the fifth power be? It would be 243. You can just figure them out on your calculator. Again, it's usually something like 2 to that power or 3 to that power. So this one, because it's a cube root of 40, I would rewrite that as cube root 8 times 5. Now the reason I picked 8 is so I can do the cube root of it. The cube root of 8 is 2. And then don't forget your index, cube root 5. This one, fifth root of 96. 96 is 32, which is 2 to the fifth power. So it's 2, fifth root, 32 times 3. Again, the reason I picked 32 is so I can take the fifth root of it and get a whole number. The fifth root of 32 is 2. Leave your index 5. Most common mistake, students, the index disappears as they start doing these. It's got to stay the same the whole question. 2 multiplied by 2 is 4. Fifth root of 3. So that's the first skill that's really important in this unit, is you're able to simplify numeric radicals. Now we're going to move on to variables here shortly, but you have to be able to do the numbers first. Variables. How do we switch variables, or how do I take the square roots of variables? Now this is why earlier on I showed you that the square root of x to the 16th. So this one, often students will say, I think it's x to the 4. Then somebody else might say, no, I think it's x to the 8th. And then hopefully if we were in class, it would lead to a good discussion and say, I don't know, which is it? I do know which one it is, but I'd like students to kind of know why it's which one. One of these is right. One of them is wrong. Well, let's get rid of our writing here for a second, and let's see if we can think this through. I showed you in the beginning that square root, right, square root of x is the same thing as x to the 1/2. Which means then, if I had the square root of x to the 16th, it would be the same thing. So instead of a square root symbol, I could just put a half as my exponent. Well then, I would multiply these exponents. That's called law of exponents, the power law. 16 times a half, x to the 8 was the right answer. Now I intentionally picked 16 to kind of almost lure you into thinking, maybe I take the square root of 16 and it should be a 4. That's why students would think it's a 4. I want you to realize that when you take the square root of an exponent, you take half of an exponent. Well, what do you think would happen if you're taking the cube root of an exponent? Anything, if you take the cube root of it, that means take a third of it. Oops, cube root of x is x to the 1/3. So here you're going to take a third of the exponent. It would be w to the 9. Well, when you have a combination here of both, so now I got to do the fifth root of the number first. So the fifth root of 32, so happens that it's a perfect whole number, it's 2. And now the fifth root of y to the 10th, that would mean raise it to the exponent 1/5. So you have to take a fifth of your exponent. It would be y squared. So don't confuse exponents with coefficients. They're done differently. Coefficient, you're trying to find a number that multiplies by itself 5 times to give you that. An exponent, if it's a fifth root, you're taking 1/5 of your exponent. Well, those three worked out very nicely. What if the exponents aren't as nice? So what if, for example, I wanted to take the square root of x to the 11th, which is a square root, which means take half of my exponent, but my exponent's not a perfect square. Well, what we're going to do is we're going to, just like we would do with numbers, we're going to rewrite this as two things that multiply together. to give 11, but I want one of them to be a perfect square, and I want it to be the biggest possible one. So I'm going to change this to x to the power of 10 multiplied by x to the power of 1. In your head, compare it to this. When you have the square root of, 12, and you split it apart into the factors 4 times 3, the reason you did that is so you could take the square root of 4. I'm doing the exact same thing here. I want to rewrite this as two things multiplied together, but I want one of them to be a perfect square, meaning I can take half the exponent. Now I can do the square root of x to the 10th is x to the 5th. X to the 1 is not a perfect square. It stays underneath there. There's x, the square root of x to the 11th in reduced form. X to the 5th, square root x. All right, 27. So what I would do in this one, I would do the number like normal. So 27 is 9 times 3. X to the 6th, I can already take half of it. Leave it like it is then. Y to the 5th, I cannot take half of that, so I'm going to split it apart into y to the 4th multiplied by y to the 1. You don't need to put the 1 there. I'm just emphasizing it so you can see that if I add those exponents, I'd still have y to the 5. Anything that's a perfect square. So 9's a perfect square. Any even exponents are perfect squares. So the three that I've underlined in red are perfect squares. We're going to take the square root of those and bring them out as coefficients. The square root of 9, 3. The square root of x to the 6th, x to the 3rd. The square root of y to the 4th, y squared. Put your radical in. This was not a perfect square, it stays under, and the y was not a perfect square, it stays under. Now I don't want to jump to 4th root yet, so let's give us more practice. So let's take the square root of 8, a to the 7th, b to the 6th, c to the 13th, and d to the 9th. And let's simplify this. Start with your 8. So I need a perfect square that goes evenly into 8. 4 times 2. 8, I can't take half of 7, so I have to split it apart into a to the 6th times a to the 1. b to the 6th, it's already even, no problem. I can't take half of 13 without getting a decimal, so it's c to the 12 times c to the 1. d to the 9th is d to the 8th times d to the 1. I will now highlight ones that are perfect squares. So 4 is a perfect square, a to the 6th, b to the 6th, c to the 12, and d to the 8th are all perfect squares. So the ones that are perfect squares, we take their square root. So the square root of 4, 2. The square root of a to the 6th, you take half the exponent. It's a to the 3rd. The square root of b to the 6th, b to the 3rd. The square root of c to the 12, c to the 6th. The square root of d to the 8th, d to the 4th. Anything that wasn't a perfect square, so the 2, the a, the c, and the d, they get rewritten under the radical. So 2 was not a perfect square, a was not a perfect square, c was not a perfect square, and d was not a perfect square. That is the reduced version of this original expression. All right, so let's try another one. This would be, again, a good chance for you. If you're doing this properly, you should not just be watching this like you're watching your favorite Netflix show. You should be stopping the video from time to time, doing examples, etc., etc. Okay, let's go with 48, and we'll go with x to the 13th, y to the 3rd, and z will be to the 1. So now I will rewrite this. So 48, I need it to be a perfect square that goes into that. The biggest possible one would be 16 multiplied by 3. There's your 48. 13's not divisible by 2, so I'm going to write it as x to the 12 times x. Y to the 3 is not divisible by 2, so I'm going to write it as y squared times y to the 1. Now z to the 1, there's nothing I can do. It's already lower than 2, so it's going to have to stay there as z. pick out the perfect squares. So 16, x to the 12, and y to the 2. Those are perfect squares. So we'll take the square root of those to give me 4, x to the 6th, y, and then square root 3, x, y, z. There you have it in simplified form. Okay, so now what we want to do is deal with higher indexes. So let's suppose the index isn't a square root, but it's a cube root. So for example, actually let's just go on our own here. So let's go cube root of 16, a to the 13th, b to the 12, c to the 5. Now, in order for exponents, let's say x to the 11th, in order for me to be able to take the cube root of it, I have to be able to divide the exponent by 3, which I couldn't do that with 11. So you have to find the closest exponent to 11, which means the biggest one, that divides evenly by 3. So you would have to rewrite x to the 11th as x to the 9th times x squared, because 9 plus 2, you add exponents when you're multiplying if the bases are the same, that would give you your 11, but now I've got an exponent that I could take, the cube root of. So the cube root of x to the 9th would be x to the 3rd. This one I can't take the cube root of, so it stays underneath here. So one thing you're going to find is that if this is a cube root, underneath here, they're all going to be lower than 3. If you have an exponent here that's more than 3, you haven't reduced it as far as it'll possibly go. Okay, so let's use that over here. So now I want perfect cubes that go into 16. So not square root, a perfect cube. So I tried to keep it easy, one you could do in your head. This would be 8 times 2. A to the 13th doesn't divide by 3, so it would have to be a to the 12. Multiplied by a to the 1. Again, you want to pick the closest one. That'll give you the biggest one. B to the 12 will already divide by 3, so don't touch it. C to the 5 will not divide by 3, so you'd have to write it as c to the 3 multiplied by c squared. Identify the ones that are perfect cubes this case. So 8, anything divisible by 3. So those that I've underlined are perfect cubes. The answer here will be 2. That's the cube root of 8. The cube root of a to the 12, you take a third of the exponent. So it's a to the 4th, b to the 4th, c to the 1. Don't forget your index. Cube root. So anything that wasn't a perfect cube stays under 2, a, and c squared. As long as this exponent is lower than your index, it is reduced. So we would be done. Okay, let's try one more like that, and then I'll let you guys do some practice on these. So let's go, we'll go 4th root, and we'll go 48, and we'll go x cubed, y to the 10th, z to the 21. All right, here I go in simplest form. I need a perfect 4th root. And you say, I don't know any. Well, make one. Take 2 and raise it to the 4th. You get 16. Will 16 go into 48? Yes, it will. That's the only one that had a chance to work, because 3 to the 4th power is bigger than 48. It's 81. So it can't be that one. The only possibility was 16, and it worked. So 16 times 3. This exponent is already lower than the index. That tells me it's already reduced. Now 10, I want to be able to divide my exponent by 4. I can't divide 10 by 4, but I could divide 8 by 4. That's the closest one to 10 that divides by 4. 21 won't divide by 4, but 20 will. So it's z to the 20th times z to the 1. Pick out the ones that are perfect 4th roots. 16, y to the 8th, z to the 20th. We're going to take the 4th root of those ones. To give me, the 4th root of 16 is 2. The 4th root of y to the 8th, so you take a 4th or a quarter of your exponent, so y squared. Divide that by 4, you're going to get z to the 5th. And these ones are not perfect 4th roots, so 3 would stay there. X cubed, y squared, and z. Those are your non-perfect cubes. Oops, sorry. And there you have it. So that's how you reduce radicals. So we've fairly quickly moved on from your basic NERF 10 reducing square roots. Then we moved on to perfect cubes, perfect fourth roots involving numbers, and then we extended that to what if there's variables as part of your expressions as well? How do we deal with those? So hopefully I've shown you enough examples that you can figure that out. All right, so as always, best of luck. This is our introduction to our unit on radicals. These will kind of be the stepping stones to get us pointed in the direction of how to add, subtract, multiply, divide, solve radical equations, all kinds of good stuff that we'll do with radicals. Thanks for watching.